our scholar at Department of Science. Okay. In last class, what we studied? We studied the thermochemical equations for the enthalpy change. Then we solved some problems related to that. After that, we studied what is heat of combustion, and then finally we studied the extensive and intensive properties and how we can differentiate between them. Okay, and these were the examples of these properties. Okay. Now we will start with the lecture 7. So in this lecture, I will talk about the heat capacity, what is molar heat capacity, then what is heat capacity at constant volume, and then we will read about what is heat capacity at constant pressure. You guys will be very this will be very easy for you because I have already told these things. That's why it will be very easy for you to understand this. What will I do? What I will teach in this. Okay. After that, we will derive a relationship between Cp and Cv. Okay. Finally, we will calculate the delta U, that is change in internal energy, and delta S, that is change in enthalpy. And then we will end this class by solving some problems. Okay. So let us start. So what is molar heat capacity? So okay, but first let me take the pointer. So what is molar heat capacity? When heat Q uh, one second, just when heat Q is supplied to a system, then what will happen? The molecule will absorb the heat. Okay, then the molecule in the system absorb the heat and hence their kinetic energy increases. What happens when you supply heat to the system? The molecules will absorb that heat and then they will use that heat, and what will happen? They will start moving. So what will happen? Kinetic energy will increase. Okay? Then which in turn raises the temperature of the system from T1 to T2. Say if initially its temperature was T1, then after supplying heat to the system, your temperature will rise due to the increase in the kinetic energy and it will become T2. This increase in the temperature, that is the difference T2 minus T1, is directly proportional to the amount of heat absorbed and mass of the substance. So this difference, that is T2 minus T1, which is nothing but the increase in temperature, this is proportional to T2 minus T1. First, it is directly proportional to the heat absorbed. Okay? It is equal to the directly proportional to the heat absorbed, that is Q, and also mass of the substance is m. Okay? So this difference, that is the increase in the temperature, is directly proportional to the amount of heat absorbed. Okay, and also it is proportional to the mass of the substance. In other words, when m is equal to 1 kg, if your mass of the substance is 1 kg and the difference in the temperature is 1 kg, if you are supplying heat Q to the system, then this system raises its temperature by 1 Kelvin. Okay, the temperature of the system increases by 1 Kelvin. And what is the system? It is system is of having mass 1 Kelvin. Then the heat capacity defined as specific heat capacity. Okay. So when you define this that you are taking when your mass is defined, okay. So for you are taking mass 1 kg, and if you are finding the mass that is 1 kg, then the heat capacity in that case will be called as specific heat capacity. So here mass equal to 1 kg, then specific heat capacity. Thus, specific heat capacity of a system is defined as what the heat absorbed by 1 kg of substance to raise its temperature by 1 Kelvin at a specified temperature. Suppose this is your system, and you have 1 kg of substance over here. This mass is equal to 1 kg. If you are providing heat to the system Q, okay, you are providing heat to the system Q, then this 1 kg of substance, will absorb heat. Okay, if it absorbs heat, then the temperature will rise. Okay, so in order to rise the temperature by 1 Kelvin, okay, in order to rise the temperature by 1 Kelvin, what amount of heat is required? So that heat is known as the specific heat capacity of a system. Okay, so the amount of heat. Okay, I'll write it over here. The amount of heat required or absorbed by, here we are specifying the mass by 1 kg of substance to increase the temperature by 1 Kelvin. Okay, we are increasing the temperature by 1 Kelvin. So if this is the case, then we call it specific heat capacity. Specific heat capacity. Okay, this is the case, we call it specific heat capacity. Okay. So if mass is defined like you are taking 1 kg of substance, then we call it specific heat capacity. What we calculate it for 1 mole of substance. If in that case, what we will call it? Because in chemistry we deal with this mole. Okay, so what we will call it? We call it molar heat capacity. Okay, so if we are taking 1 mole of substance, then it will be called as molar heat capacity, which is denoted by Cm. Capital is denoted by Cm. Okay, M represents molar, C represents heat capacity. Okay, heat capacity. This is heat capacity is represented by C. Okay, heat capacity is represented by C, and molar heat capacity is represented by Cm. Okay, so it is defined as the amount of heat absorbed by 1 mole of the substance. Okay, the amount of heat absorbed by the 1 mole of the substance to raise the temperature by 1 Kelvin. Okay, so in order to raise the temperature of a system by 1 Kelvin, the amount of heat absorbed by 1 mole of substance will be called as the molar heat capacity. Okay, and it is denoted by here you can see heat is directly proportional to mass. The heat absorbed is directly proportional to mass and the temperature difference. Okay, del T is temperature difference. It is nothing but the T2 minus T1. If this is the case, if we have to remove this proportionality sign, then we will put a constant. Okay? So then your Q will become equal to constant C into M into delta of T, which is nothing but T minus T. So here this constant C, what we call as heat capacity. So this is what is heat capacity. So if we want to calculate this heat capacity, then let us keep this C this side only and bring this M into delta T to the left side. What we will get, C will be equal to Q divided by M into delta of T. So your heat capacity is equal to the heat absorbed by a system in order to raise the temperature by 1 Kelvin by 1 kg of substance. Okay. If 1 kg of substance, then it is specific heat capacity. If 1 molar, then we will use C equal to Q by, for 1 mole, we will use N into delta T. I will summarize these equations in the last slide, so don't worry. Okay, so just we have to remember that here C is the heat capacity and it is equal to Q by M. M is mass here, case of heat capacity, and delta is the temperature difference, which is minus. This equation will become Q by M into T minus T is the equation for the heat capacity. Okay. So now we are clear with the specific term, specific capacities and molar heat capacity. Let us move to the next slide now. Okay. So what will be the unit of heat capacity? So this is very important. So if I am asking you to use the units of specific heat capacity, in that case, this is your Q is nothing but the energy, okay? Heat. So the unit of heat is Joule. So the unit of Q will be Joule. Okay. Then we have M. M in this case is mass. In case of specific heat capacity, it is mass. And SI unit of mass is kg. So we will write kg over here. Next, we have the temperature difference, delta T. And unit of temperature is, SI unit of temperature is Kelvin. Okay. So we will write Kelvin. So what will it become? It will become Joule, which is denoted by J, per Kelvin. Okay, Joule per Kelvin per kg. Okay, so this is the unit for specific heat capacity. And what will be SI unit for the molar heat capacity? And for molar heat capacity, Q by N into heat delta T. So if this is the case, unit of Q is Joule and unit of mole is mole, and delta T for temperature it is Kelvin. So it will become Joule per Kelvin per mole. So it is nothing but Joule per Kelvin per mole, which is written over here that the unit of heat capacity SI unit of molar heat capacity is joule per Kelvin per mole. So these molar heat capacities can be expressed in two ways. We can calculate it at constant volume, and we can also calculate at constant pressure. So if we are calculating molar heat capacity at constant volume, we will denote it as CV, where V represents volume, that means at constant volume. And if we are calculating molar heat capacity at constant pressure, then we denote heat capacity by Cp, here P means pressure. So molar heat capacity at constant volume is denoted by Cv. C represents heat capacity and V at constant volume. And next, molar heat capacity at constant pressure is equal to Cp. Now we know that from the first law of thermodynamics, your U is Q plus W. Okay, and if this is the case, we know that your W, that is work done, is equal to minus of P. If we arrange this equation, then we will get Q is equal to U, and if this minus P dV goes to the left side, it will become plus dV. Okay, so your Q will become U plus of P dV. Okay, so this, you will get this equation, and if we differentiate this equation with respect to temperature at constant volume. Okay, let us just differentiate this equation 7.19 with respect to temperature at constant volume. So it will become PQ with respect to temperature. So it will be dT. So we are differentiating it at constant volume. So we will write volume over here. If it represents, we are differentiating it at constant volume. Now this is the left hand side. What will be the right hand side? Du by dt at constant volume. So if volume is constant, that means if volume is constant, that means your volume is not changing. If volume is not changing, then that means del V, that is minus 1, will be 0. Okay. If dV is equal to 0, then your P into dV will all become 0, because multiplying 0 with any term, it will give the whole term as 0. So here this will become 0. So now we are left with dq by dt at constant V is equal to du by dt at constant V. And this excuse me, we know that C, your C is Q by T. Q by delta T is your C. So if this is the case, then this will become C of CV. Okay, this this term will become CV. Okay, so this CV is equal to nothing but dq by dt at constant is nothing. The amount of heat uh, absorbed by a substance in order to increase the temperature by dt at a constant volume. Okay, so if this is the case, then this will become, then what will become? This will become CV. So it will give you CV is equal to du by dt at constant T. Okay. So this CV is nothing but your molar heat capacity at constant volume. Okay. So now we have the question for CV. So this question will signify something. So what does it signify? It signifies that the heat capacity at constant volume is defined as the rate of change of internal energy with respect to temperature at constant volume. So it is defined as the rate of change of internal energy, that is with respect to temperature at constant volume. This is nothing but the heat capacity at a constant volume. Okay. Similarly, if you want to calculate the molar heat capacity at constant pressure, okay, then it is Cp, because molar heat capacity at a constant pressure will be nothing but dq by dt at constant P, which will be Cp. If this is the case, then your Cp is equal to dH by dt at constant P. So this is the expression for Cp, that is molar heat capacity at constant pressure. So these expressions are very important. You must remember it, that Cp is nothing but the change in rate of change of internal energy with at constant volume, and Cp is the rate of change of the enthalpy with temperature at constant pressure. Okay? It is nothing but the rate of change of enthalpy, that is dH, with respect to temperature at constant pressure. Okay? This is your molar heat capacity at constant pressure. Let us now derive the relationship between the Cp and Cv for an ideal gas. Okay. Before that, I would like to mention a point, that your heat capacity. So I will write it over here. This is very important. Your heat capacity is an extensive property. In last class, we have studied what are. So your heat capacity is an extensive property. But if we are taking specific heat capacity, so now we are defining the mass. Okay. So if we are defining the mass, then it will become an intensive property. Okay. So specific heat capacity. And also, in case of molar heat capacity, we are taking the heat capacity per mole. Okay? And if we are taking it per mole, then it will also become an intensive property. We know it very better that if we divide two extensive properties, then the result will be an intensive. Okay? So specific heat capacity and molar heat capacity are intensive properties. These are intensive. Okay? Yeah, this was the point I I was trying to mention. Okay, let us now derive the relationship between your C and P. We know that enthalpy H equal to U plus PV. We also know that for 1 mole of an ideal gas, or 1 mole of an ideal gas. In case of ideal gas, your PV is equal to nRT. Okay. So what will this equation 1 become? Equation 1 will become H equal to U plus nRT. And if we differentiate this equation with respect to temperature, differentiating this equation, with respect to temperature, with respect to temperature, what will we get? dH by, with respect to temperature, it will become dH by dt equal to du by dt plus d by dt of d by dt of nRT. So what will it become? dH by dt equal to du by dt plus your n is 1 mole. Okay, n equal to 1 mole. So we will put n equal to 1 over here. So what we will get? RT. RT. Okay. R is your gas constant. So it will come out and it will become R dt by d by dt of T. Okay. You know that dH by dt is nothing but Cp and du by dt is nothing but your Cv. Okay. Plus d by dt of T will be 1. So we will left with R here only. Okay. So it will become R because d by dt of T is equal to 1. Okay. So we will get R over here. If this is the case, this is the relationship between Cp and Cv, and if we arrange it, what we will get? Cp minus of Cv equal to R. So this is the your relationship between the molar heat capacity of constant volume and constant pressure, that is Cp and Cv. At constant pressure processes, a system has to do work against the surroundings. Here, you can see that your Cp is equal to Cv plus of R. That means your Cp is greater than your Cv. Okay, because we are adding a gas constant R, which is positive. That means your Cp is greater than Cv. This equation implies that Cp is greater than Cv. So why so? So if this is why, because at a constant pressure processes, if this is a system and this a process is happening at a constant pressure, then if the pressure is constant, then if we want to rise the temperature, okay, so we have to work against that. Okay, so in order to work against that pressure, more heat will be required. So if more heat is required, then that means in that case your Cp will be more. That's why your Cp is greater than Cv. Okay, so here it is written that at constant pressure, a system has to do work against the surrounding. Okay, your surrounding is applying pressure. Okay, so this pressure is constant. Okay, So now your system will have to work against the surrounding. Okay, so in order to do that work, more heat will be required. Okay, and if more heat is required in order to rise the temperature, okay, then your Cp will be greater than your Cv. Okay, that's why your Cp will be greater than Cv. Then the system would require more heat to affect the given temperature rise than at constant volume. So Cp is always greater than Cv. Okay, so always remember that your Cp will be always greater than Cv. And by how much amount? By R. So we are left with two expressions. One is Cp minus that your Cp will be always greater than Cv. So this is the relationship between your Cp and Cv. Now let us move to the next slide and calculate delta U, that is changing in internal energy, and the delta S, that is changing in health. And in earlier classes, I have mentioned many times that if first one is one second. So in the previous lectures, I have shown that heat supplied to the system at constant volume is equal to nothing, is equal to change in internal energy. And if it is supplied to the system at constant pressure, then that is equal to the change in enthalpy. Okay, so in earlier classes, I have told you that heat supplied to a system at constant volume is equal to the change in internal energy. And that means heat supplied at a system at a constant volume, that is QV, is equal to change in internal energy. And also heat supplied to a system at constant pressure is equal to the change in enthalpy. Okay, that means Q at T is equal to delta of. Okay, so this will help us here. So for if we are taking for 1 mole of an ideal gas, we have Cv is equal to du by dt. Okay, here we have this expression. Yeah. Here Cv and here Cp. Cv is equal to du by dt and Cp is equal to dh by dt. Okay. If your Cv is equal to du by dt, okay, then if we calculate du, what will it become? Cv into, here it is in division, it will go here and it will be multiplied over here. So your du will become Cv into dt. So this is at constant volume. Okay. And we know that heat supplied to a system at constant volume is equal to the change in internal energy. If this is the case, then you take this du is nothing but Q at V. This is the expression for du and Qv, which are equal. So you can also write this CV as, if du is equal to your QV, then you can write, with replacing this du with QV, write this by dt. Okay. Similarly, your Cp is equal to dH by dt, and if we calculate dH, we will get Cp into dt. Here pH is equal to Q at P. Let us write it over here. Then your Q at P constant pressure will become Cp into dt. Also, if we replace this dH with Q at P, then we get Cp is equal to by. Okay. So these are the expressions. This will help us in solving problems. Okay. Let us come here. For a finite change, we have here we were considering 1 mole of gas. Now let us consider n moles of gas. So in that case, and your temperature is getting changed from T1 to T2. In that case, we are taking n moles of gas. Cv will be as such, and your delta will become T2 minus T2, that is minus minus 3. So for n moles of an ideal gas, what we will get? Delta U will be n Cv T2 minus T1. Okay. So this is for 1 mole of ideal gas. This expression is for 1 mole of ideal gas. And what if we take n mole of ideal gas, multiply this expression with n. So what we will get? Delta U n Cv, that is T2 minus T1, and delta is n Cp into T2 minus for n mole of an ideal. So this is how we will calculate delta U and the values of Cp or Cv is given, and the temperature difference is mentioned, or the initial and final temperature is given, and the moles are given. And if it is not given, then we will have to calculate the moles. So this is how we will calculate delta U and delta H value. Now let us move to the next slide and solve some problems Hybrid asked on the basis of this expression. Okay. We have to calculate here delta U and delta H. Question is, calculate the values of delta U and delta H on heating 128 gram of oxygen. So here they have given weight, okay, 128.0 gram of oxygen. Okay. From 0 degree Celsius to 100 degrees Celsius. So they are increasing the temperature by 100 degrees. Initial temperature T1 is 0 degree Celsius, and if this is the case, we change this 0 degree Celsius in Kelvin. What we get? 0 plus 273, that means 273 Kelvin. So T1 is 273 Kelvin. T2 is 100 degrees Celsius. Let us change this degree Celsius to Kelvin. So 100 plus 273 will give us 373 Kelvin. So your T2 is 373 Kelvin. Okay. Now they have given us the value Cv and Cp on an average are 21 and 29 respectively. Cv is 21 joule per Kelvin per mole, and Cp is 29 joule per Kelvin per mole. So now what we have to calculate? Delta U and delta H. So this See, this is very easy way. First, you have to write what we have to calculate. We had to calculate delta U and delta S. Then we will write what is already given. So these values are all given to us. Okay? Now let us see how can we solve this question. So we have to calculate delta U. We know that delta U is NCV dt, and if we expand it, dt is nothing but T2 minus T1. So in order to calculate delta U, we must know the value of N, CV, T2 and T1. So T2, T1 we know, CV we know here, CV, T1, T2 we already know this value. Now we have to calculate the value of N. Okay. So let us calculate the values of N. That is number of moles. We know that number of moles N equal to given mass upon molar mass. Given mass divided by molar mass. We have given 128 gram of oxygen. What is the molar mass of oxygen? 32. Okay, so this will be our number of moles. That means 4. Okay, so if we divide, we will get 4. So your N will become 4. So now we have calculated N. So let us put the value of N, that is number of moles, CV, T2 and T1 in this expression 1. Then we will get the value of delta U. Delta U is equal to N CV T2 minus T1. N is equal to 4. Your CV is 21. Okay, your CV is 21. T2 is your 373 Kelvin minus your T1 is 273 Kelvin. Okay, and your CV was in Joule per Kelvin per mole. Okay, I will write its unit over here. Joule per Kelvin per mole. Let us solve this. 4 into 21 into 373 minus 273 will be nothing but 100 into Kelvin. Now we have Joule per Kelvin per mole. So this per Kelvin and Kelvin will cancel out, which will give us 4 1 4, 4 2 8 into 100 Joule per mole. Your delta U will become 8400 Joule per mole. But here we have calculated for 4 mole. So here we are calculating for 4 mole. So your per mole will not be considered over here. Okay. Okay. So we had N is equal to 4 mole. So if 4 mole will be here, then I will write it. Okay. So then this mole and this mole inverse and mole will also be cancelled out. Okay. This mole and mole inverse will be cancelled. So what will be left with? Only Joule. So we will be left with only Joule. Okay. So if this is the case, then you delta U. If this is Joule, in order to change it to kilojoule, we will divide it by 1000. So if we divide it by 1000, it will become 8.4 kilo. So this will be your value of the change in internal energy. Now let us calculate the value of change in enthalpy. Okay. Now if you want to calculate the change in enthalpy, so change in enthalpy is nothing but delta T, that is NCP into T2 minus T. And we already know 4. Okay. Your CP value is given 29. And T2 is 373 minus T1 is 270. Now let us calculate this. 4 9 is 36 and 3 4 to 10 9 15 11. 116 into 373 minus 273 will be 100. So it will become 11600 11,600 joules. So if we divide it with 1000, so we will get it in kilojoules. By dividing it with 1000, we get it value in kilojoules. So this is the value of your delta S, that is changing in cell and changing in internal. So this is your answer. So the answer I write over here that delta U is and delta H equal to 0. This is your answer for this. Now let us solve the next. So here they have asked that at constant volume, to raise the temperature of 5 mole of oxygen from 10 Kelvin to 20 Kelvin, how much heat is required? While at constant pressure, molar heat capacity is 7 calories per Kelvin per mole. So we have in order to raise the temperature from 10 Kelvin to 20 Kelvin, initial temperature is your 10 Kelvin and final temperature, that is T2, your 20 Kelvin. And here we have given number of moles. Number of moles equal to 5 moles. Okay. So 5 moles of oxygen from 10 Kelvin to 20 Kelvin. How much heat is required? So heat required at constant volume is QV, and we know that QV is equal to delta of U. And if this is the case, we have already calculated in the previous problem that delta U equal to N CV delta T, which will become N CV delta T is T2 minus T1. Now let us calculate the delta U. Number of moles is given 5 CV. Okay. We have to calculate the value of CV. We have given the value of heat capacity, molar heat capacity at constant pressure, which is nothing but Cp. Cp is given 7 calories per Kelvin per mole. If Cp is given, then let us calculate Cv. So we know that relationship between Cp and Cv, which is nothing but the Cp minus Cv is equal to R. Now your Cv will become Cp minus R. If this is the case, your Cp is 7 minus R is 2 calories per Kelvin per mole, then your Cp will become 5. Okay? So your Cp will become 5 calories per Kelvin per mole. So now we have the values of N, Cv and T2 minus T1. Let us just put this over here or in this equation and solve. Cv is 5, T2 is your 20 Kelvin and T1 is 10 Kelvin. 5 into 5 will be 25 and 20 minus 10 will be 10. So this will become 250 and these values were given in calories, so it will be in calories. Okay. So your change in internal energy will be 250 calories, which is nothing but the heat required at constant volume. So the answer will be heat required at constant volume 250 calories. Okay. Uh, Now let us move to the next. Here again, we have asked to calculate the heat. In order to raise the temperature of 1 mole of gas, here N is equal to 1 mole from 400 Kelvin to 500. Okay, so T1 initial temperature is 400 Kelvin and T2 final temperature is 500. So we have to calculate how much heat is required. If your Cp is T plus 1.2 into 10 to the power minus 3 into T calorie per mole. So we have to calculate the heat required at constant pressure. And we know that heat required at constant pressure is Qp, which is nothing but delta H. And if this is the case, we know that delta H is equal to N into delta T will become NCP T2 minus T1. But here your Cp also depends on T. So the calculation will be little different. And so we will write delta H here as integration of T1 to T2 NCP T2. Okay? Because here your Cp is also depending on temperature. So let us calculate. So delta H T1 is 400 Kelvin, T2 is 500 Kelvin. T2 is 500. N is 1 mole, so there is no meaning of adding more here. So Cp, let us write the value of Cp is 3 plus 1.2 into 10 to the power minus 3 into T. I'll just add a slide because it is a long problem. So we need some space to solve the question. So let me just add a slide. So we were here delta H equal to integral of 400 Kelvin to 500 3 plus 1.2 into 10 to the power minus 3 T into dt. Let us expand this. So we will get 3 into kt plus of integral 400 Kelvin to 500 1.2 into 10 to the power minus 3 T into dt. Okay. Next, this T is constant, so we will take it out, and the integral of dt is nothing but T. So if that is the case, we will write T over here because integral of dt is T, and it is changing from 400 to 500. Next, we have 1.2 into 10 to the power minus 3. This is constant. Let us take it out. Now we will be left with the integral of T into dt. So this will become 3 into This value minus this value. So 500 minus 400 plus 1.2 into 10 to the power minus. We know that integral of t is t square by 2. If we put it over here, then what we will get? T square by 2, 400 Kelvin. Integral of dt is equal to t. Now what we will get? 500 minus 400 is 100. So multiplying it with 3, we will get 300 plus 1.2 into 10 to the power minus 3. 2 is constant. Let us take it out. Now we will be left with t square 400 to 500. It will become, now let us solve this. It will become 0.6. So 0.6 into 10 to the power minus 3 t square. T square will be nothing but your upper limit का square minus lower limit का square. Here upper limit is your 500, then 500 का square minus lower limit is your 400. 400. If you solve this, you will get, let us write it like 6. If we write 6, then it will become 6 into 10 to the power minus 1. Right? Want to write 0.6 as 6. Then we can write it as 6 into 10 to the power minus 1. Here 10 to the power minus 3 is already here. So if 6 into 10 to the power minus 1 into 10 to the power minus 3 is there, then power, if base is same, then what we do? Then we add the power. So if we add the powers, then what will become? Minus 1 minus 3. Then what will we get? 6 into 10 to the power minus minus it will become plus. So 3 plus 1 will be 4 and the sign will remain minus. If we write 0.6 into 10 to the power minus 3, we can write it also as 6 into 10 to the power minus 4. Write it as 6 into 10 to the power minus 4. Now 500 square is nothing but 25,000 minus 400 square will be this much. This we can write as 10 to the power 4. So it will become 300 plus 6 into 10 to the power minus 4. 25 into 10 to the power 4 minus 16 into 10 to the power 4. So here 10 to the power 4 is common. Let us take it out. So it will become 300 plus 6 into 10 to the power minus 4 into 10 to the power 4, and in bracket we will be left with 25 minus 16. Now 300 plus, if base is same, then what we do? We add the power 10 to the power minus 4 into 10 to the power 4. Okay. So if base is same, then we add it. So 10 to the power minus 4 plus 4 is 0, and something to the power 0 is 1. So we will write it as 1. So 6 into 1 into 25 minus 16 is 9. So it will become 9 6 are 54. So it will become 50. So your CP was given in calories. Your CP value was given in calories, and we have done all the calculation in calories. So what will be your delta as in calories? So your answer will be the heat required at constant pressure that is delta H, or also it can be QP, is equal to 354 calories. Okay, so this is your answer. Okay, so this was the last question I had. Okay, now in this class, what we studied the heat capacity. Then we studied what is molar heat capacity, what is specific heat capacity, and then we have gone through the SI unit. Okay, after that we derived the expression for this CP and CV. Okay, and after that we derived the relationship between them, and then we calculated the delta U and delta S values, and after that we solved these problems based on this. So this is what we solved today. Okay. Okay. So in next class, what we will study, we'll study how we can measure the delta U and delta H values using calorimetry. Then we will read about bomb calorimeter and its principle and working. Okay. So in next class, I will cover it. Okay. So this is the end of the session. I will end this class now.